Okay, so first up we'll have Jim Posen from Ulvetanna talking about Binius.
All right. I guess I should have this. Hello, everyone, and thanks for being here bright and early. I'm Jim Posen. I'm one of the co-founders of Ulvetanna, and we are a company focused on cryptographic acceleration of zero-knowledge and verifiable computing. We do this through a combination of cryptographic innovation, high-performance engineering, and building custom compute with FPGAs. And this combined hardware-software perspective is what led us to investigate binary fields and develop a new SNARK protocol called Binias, which we believe will ultimately reduce the cost of verifiable computing by at least another order of magnitude for practical use cases. To set a little bit of context, that we're all here to build decentralized infrastructure, and basically we're in the midst of a ZK zero-knowledge revolution. At a minimum, SNARKs, that didn't work. At a minimum, SNARKs add a really necessary security layer to decentralized protocols, much like HTTPS added a layer of security to the internet, but it actually unlocks a lot more. Large-scale deployment of SNARKs can unlock light clients usable on mobile devices, cheap transactions, interoperability, permissionless innovation on L2s, better oracles for off-chain authenticated data, and amazingly, we can get all of this without sacrificing security or trustlessness. Let's see. And so in order to do this, we need proving performance to be good enough to be practical. And once proving performance is there and is no longer a bottleneck, I believe SNARKs will be used throughout all decentralized protocols, just the way that HTTPS was widely deployed on the internet in the last 15 years. So where are we today with proving performance? Let's look at Keccak as a guiding benchmark because it's the #1 bottleneck in ZK-enabled protocols for scaling Ethereum. We'll look at Scroll's Halo 2 versus Plonky 3. Scroll's Halo 2 uses elliptic curve commitments, uses the KZG commitment scheme, and Plonky 3 uses Fry over a 32-bit prime field baby bear. And here's some benchmarks that I ran on my computer. We can see that the proofs for Halo 2 are about 50 times smaller, but the proving performance is about 20 times worse. There's 2 rows for Plonky 3. You can either use Keccak as the hash function for the Merkle tree or Poseidon 2, which can give you better recursion. And we need to understand a little bit about where a prover will spend its time. There's basically 4 steps. You generate the witness. This is not particularly expensive, but it is difficult to parallelize, or more difficult to parallelize. You have to commit the witness, which in the case of Plonky 3 and STARKs is basically NTTs or Reed-Solomon encoding plus Merkleization, and in the case of Halo 2 is MSMs. There's the vanishing argument, which is, for both of these, some sort of polynomial divisibility check, and in the case of multilinear protocols like Binius, it's the multivariate sum check protocol. And then you have the opening proof, which is sort of where the magic happens. It's kind of the most complex step, but actually typically doesn't account for too much of the proving time because you can amortize this through batching of multiple commitments together. So we can look at where Plonky 3 spends its time as sort of a guide, and what we see immediately is that committing accounts for the majority of the time. It's almost 50% even when you're using a fast hash function like Keccak, and it's 75% with Poseidon 2. This profiling is done single-threaded to kind of show truly where the compute is required. And so to get faster provers, we need to tackle this commitment issue. And that brings us to Bineas. So Bineas is not technically a STARK, but it does use Reed-Solomon codes and hash functions, much like Plonky 3. The main difference is that instead of using a 32-bit prime field or a 64-bit prime field, we use binary fields. And specifically, we use a construction called towers of binary fields. And I'll explain the importance of that. The other big difference is that we use a multilinear polynomial IOP, similar to Hyperplonk, instead of the Deep Ali protocol that STARKs use. And we have a new commitment scheme that gives us pretty remarkable properties with binary fields. There are a couple of other contributions in the paper that I won't have time to get into. And basically my main goal here is to convince you that binary fields, and specifically towers of binary fields, are the right primitive to use for fast verifiable computing. I say fast to say that we can't necessarily achieve the smallest proof sizes, but through recursion we could. But fast verifiable computing is very important, and the reason we can achieve, I believe, binary fields are the right primitive is for three reasons. One, the arithmetic is just faster in native digital logic. The compute complexity is lower. Two, they're very friendly and widely used in symmetric cryptography already, both in terms of implementing symmetric cryptography and snarking it. And third, there's this concept of embedding overhead in arithmetization, which essentially is how much, what is the information density of your committed data? So we saw how expensive commitments are. We want to improve the information density of our committed data. So starting with the story around arithmetic, I should have set a timer, but so oops. Okay, what is a binary field? So the smallest binary field is F2. It's the integers mod 2, so basically bits. We can also look at larger binary fields. So let's take a string of, say, 128 bits. This is an element of GF2 to the 128. And addition of all binary fields is the XOR operation. Multiplication is a little more complicated. It's basically, we can interpret this string of bits as a polynomial over F2, and multiplication is multiplication of polynomials modulo some irreducible. So for example, we could choose the 128-bit prime field to be modulo this particular irreducible. This is called the polyval field. And we don't need to exactly understand how this works. It's very similar to large integer multiplication, except that the multiplication and addition is carryless, and this has important implications for circuit design. So one thing that we know about, say, the 128-bit binary field is that it contains subfields which permit faster multiplication, but we need a different representation of this field in order to take advantage of this. So we're going to look at a tower of fields, and what this means is we can take a single 128-bit binary field, or we can take 128 bits and view it either as a 128-bit field element, or view it as a vector of two 64-bit field elements, or as four 32-bit field elements, or so on down to 128 1-bit field elements. And we can do all of this with the same memory representation. It's basically a typecast between these different packed field representations. This also lets us support multiple data widths in our arithmetization, which is useful for range checking values. And the other benefit is that using small fields gives you proportionally better performance for multiplication, because multiplication is roughly up to quadratic, or something like n to the 1.5 using Keccak-256 techniques. So towers of binary fields have a lot of benefits in our setting. To say just a little bit about how you implement this stuff on CPUs, there's some special instructions for carryless multiplication that's useful for implementing the polyval field, which is already used in AES GCM SIV mode. And then there is a new set of instructions from Intel called the GFNI, Galois field new instructions, I believe, that let you do 8-bit binary field multiplications natively, which we're able to take advantage of. We can actually use the polyval field too, even though it's not a tower field, by explicitly computing the isomorphism from the 128-bit tower field to polyval in cases where that makes sense for us. So here's some CPU benchmarks on just multiplication. We're going to show the benchmarks for multiplying 128-bit field elements, which becomes the bottleneck in the vanishing arguments, either deep Ali or especially the multivariate sum check protocol. And as we can see here, the tower field multiplication with some optimizations that we're working on merging is competitive with, or actually beating 256-bit integer multiplication and is competitive with RISC Zero's quartic extension of Baby Bear, but is much slower still than the quadratic extension of Goldilocks. However, the polyval field is actually nearly as fast as the quadratic extension of Goldilocks, which leads to some hope that we can use that. And the story is just much better when we look at FPGAs and native digital logic. So we implemented some of these fields on FPGAs, and the way we should interpret this is it's not quite the same as looking at CPU benchmarks. We need to look at two things. We look at the area that it takes to implement the circuit, which is the resource utilization, and we look at the clock frequency. So because binary field multiplication and addition is carryless, you can clock the device, or basically you can run at a higher clock speed. The propagation delay is lower. And so we can use the metric of the number of logic gates times the delay as this measurement, performance measurement, and we see that the 32-bit binary field is 5 times more efficient than even Mersenne, which is basically the most efficient 31-bit field you could hope to have. And it gets even better when you look at 16 bits, which we are able to leverage in the polynomial commitment scheme for Reed-Solomon encoding. This is what it looks like for when you put this all together into NTTs. The main column we care about here is the gate count, which is essentially what are the resources required to sustain a throughput of 512 bits per cycle at 250 megahertz. We're looking like 4 times better than 4 times fewer resources for the NTT over the 32-bit binary field than the Baby Bear field. And moving along, the application into symmetric cryptography. So essentially, most symmetric cryptography is natively implemented with bitwise operations, so having fields that natively support XOR is extremely powerful. Bitwise AND is simply multiplication in F2, and actually there are standardized symmetric crypto primitives such as AES, and Grostel is, say, a semi-standard. It was a SHA-3 finalist based on AES that actually use the 8-bit binary field, which means we can get better arithmetization of this Grostel hash function than, say, SHA-2. Also, AES GCM uses the 128-bit binary field. And the other reason that this is really attractive for symmetric cryptography is, unlike prime fields, there's no non-canonical representations of elements. Any, say 32 bits uniquely determines a 32-bit binary field element, and so you can just typecast, say, bytes to GF2 to the 8 elements like AES does. I basically don't want to spend a lot of time on this, but this isn't some niche use case. Verifying symmetric crypto and hash functions is an essential use case of SNARKs. This basically shows how much better native hash functions are than arithmetization-oriented hash functions over prime fields. So Grostel is something like 10 times better than these Poseidon variants. SHA-2 has special hardware acceleration instructions. And I want to talk about the embedding overhead. So the question basically is, can we commit small field elements faster than large field elements? And the answer is sort of yes, with caveats for elliptic curves. And basically, this is why small field STARKs are faster than large field STARKs. However, we need to be able to get down below 32 bits, and that's very difficult to achieve with Reed-Solomon in the prime field setting. And so we can look at the arithmetization of Keccak in the starky system as an example. They use a 64-bit prime field, but the majority of the values that are committed, 2300 out of 2500, are 1 bit. So you sort of have an immediate loss of 64x efficiency. When we look at the Binius polynomial commitment scheme, which is able to eliminate the embedding overhead during the commitment phase, we see that we basically get linear scaling in the size of the committed elements, which is just not the case for Fry and Goldilocks. So for committing 1-bit elements, it's much, much faster than all the alternatives. Even though committing 32-bit elements becomes equal or comparable. Briefly, what does this look like? How do we achieve this? So in breakdown, what you would typically do is you would take this matrix of committed elements, and you would take a linear combination, or you would encode each row, taking each bit as a discrete element. But instead, we're going to pack consecutive chunks of 16 bits into a larger field element, like a 16-bit binary field element, and encode those. And a major contribution of the Binius paper is to show how to generalize breakdown so that the proximity testing phase of breakdown can do a consistency check on blocks of 16 elements at a time instead of one element, which gives you a secure PCS without too much of a trade-off, and still allowing us to use Reed-Solomon codes over an alphabet that's smaller than the size of the encoded code words. Okay, so now we want to return to this Keccak benchmark and show that this is real. So as of this morning, we merged code to do a Keccak example in the Binius code base. And so, oh, sorry, these prover times were from an old slide, but I think on the next slide they're right. So right now, with many more optimizations to come, we're able to prove 4,096 Keccaks in 13.16 seconds on this laptop with Binius, which is almost as fast as Plonky 3 is able to do with the Baby Bear field. I will note that there are many optimizations to multivariate sum check to come, and I also want to show the difference in terms of where Binius is spending its time. So we saw before that Plonky 3 spends a ton of time in commitments. Binius, to the contrary, spends nearly all of its time in the sum check protocol. So we've basically eliminated the cost of committing for circuits such as Keccak, which are natively bitwise, and so that is going to be, the focus of our optimization effort, which is applying small field optimization techniques to the sum check protocol. I think that's pretty much all I got.
Do we have any questions from the audience?
Thank you for that. I think Binius is awesome. Just put that out there. But I always have the first question, as you mentioned very early, was you think it's like HTTPS, as in ZKBs will be run everywhere at some point. What is the space efficiency of something like Binius? Will it be able to run on local computers, or will it always need kind of a special hardware setting?
So actually, even in the hardware setting, we almost care more about space than on CPU provers, because memory on the devices is more expensive than, or high bandwidth memory is more expensive than like DRAM on a CPU or something. So the short answer is, in a world where recursion overhead is very low, which is pretty much where we live now, it is a choice of the maximum memory requirements, and we're targeting proof systems that require less than 16 gigs of RAM. And I think you could push it more aggressively than that for local, ZK SNARKs.
Awesome. The follow-up would be, what is the recursion overhead of something like this?
We are trying to find that out as soon as possible. I think having this example of a hasher for Keccak is the first step, and then our roadmap is to implement the verification logic for Grostel, which should have even lower arithmetic complexity, and then we can start building a recursive SNARK in Binius.
One quick question.
Talking about recursion, so you want to do that purely with the breakdown Binius setting, or do you considering also Fry over binary fields or similar constructions?
Yes, we are looking at Fry. Fry. So There's different trade-offs. Breakdown is more prover efficient, and especially the fact that we can use faster Reed-Solomon encoding over the 16-bit field alphabet is very nice. Fry gives a much better kind of trade-off space between prover efficiency and proof size. So we are exploring that, and we'll have more to say on that, pretty soon.
Okay, we can't take any more questions due to time, but let's thank Jim again. And